Okay, so our next speaker is Luca Marchetti, who will tell us about scalar cosmological perturbations from full quantum gravity.
Okay, hello everybody. Thanks to the organizers for having me, and thanks to you all for being here, despite being the second to last talk of the conference and being the day after the conference dinner. So I do appreciate it. So yeah, I'm going to talk about scalar cosmological perturbations from full quantum gravity. And as you can imagine, it is not an easy task to... That doesn't work? Is it my fault? Oh, okay. That works. Okay. Yeah, so it's not an easy task to extract cosmological perturbations from full quantum gravity. And in fact, it's not an easy task in general to extract continuum physics from quantum gravity. So trying to go from this microscopic quantum gravity description to a macroscopic one. And we've seen that there are several obstacles when trying to go from one side to the other. A couple of them that are especially relevant for the context that I'm going to talk about are the localization problem that Bianca told us about, and the continuum, which is of course there for any background independent quantum gravity theory, but also the continuum limit problem, which is especially important for quantum gravity theories whose fundamental degrees of freedom are pre-geometric in nature. But there are still ways to address these problems. You could implement a relational strategy to address the localization problem, or you could perform some form of cross-graining to address the problem of the continuum limit, for instance, through some renormalization group analysis. But it is especially difficult to implement these strategies in full quantum gravity, both for conceptual and technical reasons. But Daniele showed us today that it is actually possible to do that in group field theory, at least in an effective sense, by choosing some appropriate collective states, which allow us to bridge between this microscopic description and the macroscopic one. So let me remind you very, very briefly how the whole strategy works. Let me remind you a couple of facts about these group field theories that also Andreas reminded us about. So first of all, the quantum group field theories are tetrahedra, can be seen as tetrahedra, which are decorated with discretized field data, and that could be gravitational field data, but also matter field data. And in particular, we will be interested in those, in particular in scalar fields in the following. And also the quantum gravity processes, so the process of these group field theories, can be seen as dual to discretized spacetime. So once you actually compute the partition function of the theory in terms of a sum over Feynman diagrams, what you obtain is a description of the simplicial gravity path integral. So the second step is the choice of states, and Daniele argued, and also Andreas, for condensate states. And they're particularly nice because they allow us to implement this notion of relationality effectively by picking the condensate wave function on the variables that we want to use as a physical reference frame. But they also allow us to implement the simplest form of coarse graining, as Andreas showed us, like this mean field approximation, so evaluating the partition function around the saddle point. And through this choice of states, one can then go to a macroscopic description, which is based on averages of collective observables and averages on these condensate states. And collective observables here in the context of group field theory can be translated as one-body operators in the group field theory Fock space. And then you can make contact with continuum physics, in particular with cosmological ones. And Daniele told us that the level of homogeneous and isotropic geometries, you have singularity resolution at early times under quite general conditions, and a classical limit at late times, which happens because essentially at those late times, the number of quanta in your condensate is quite large, and that suppresses all the quantum fluctuations that Andrea told us a couple of days ago. And you can also have a quantum geometric acceleration phase that could be associated to inflation or potential dark energy components. But here I'm going to instead move more towards the inhomogeneous side of the story, because of course there's a very rich physics that is related to these cosmological inhomogeneities, and most importantly, we have very precise observations of those. So it is particularly important to look at this. And I will show you in this talk how to describe inhomogeneities from this full quantum gravity in the context, again, of group field theories, what kind of dynamics they satisfy, also compared to GR, and maybe if I have time, I will say a couple of words about how to extract the next steps that are going to be needed to go more towards observations. So let me start by describing the system that I have in mind, which is the simplest slightly relational inhomogeneous system, which is made of 4 minimally coupled masses and free scalar fields that we want to use as a physical reference frame, and 1 matter field, which is expected to be dominating the energy momentum budget of the universe, and which is slightly relational inhomogeneous with respect to our rods. At the quantum level, we have our group field theory, and this is going to be an EPRL-like model that we're going to consider. And we'll see that, oh, sorry, that was not supposed to happen. Oh, no. A lot of spoilers. Yeah. OK. OK. So you see that we have the group field theory field that depends on our gravitational variables and on our matter variables. And since we're considering EPRL-like model, these group field theory tetrahedra are space-like in nature. And this is a technical point, but it will become important in the following. So try to keep it in mind. One of the important ingredients of the description that I mentioned before were observables. And as I said, these are one-body operators in the group field theory Fock space. And you can have scalar field operators. So we can have frame operators and matter field operators. But of course, we would also have to look at geometric observables. And we've heard about the loop quantum gravity volume operator. And that can be translated into the group field theory context and turned into a collective observable as well. So we can look at this volume operator. But notice that restricting to volume information means that we're already restricting only to isotropic information, which is an important restriction, but allows us to make some step forwards. The second important ingredient are states. And as I said, we're focusing on condensate states, which are peaked around the values of our physical reference frame, which can be achieved if you assume that the condensate wave function factorizes into a peaking function, which is fixed, and a reduced wave function, which is instead dynamically determined. And here, a couple of more technical assumptions that the peaking function is supposed to be isotropic in the peaking of the rods, and the reduced condensate wave function instead is supposed to contain isotropic information with respect to this geometric data as something that is, and this is a constraint that is imposed at the level of the representation labels associated with these group variables. Then how do we describe inhomogeneities? Well, the simplest way in which we can do this is at the level of the reduced condensate wave function. So we assume that both its modulus and its phase split into a background part, which is only time dependent, and some small perturbations, which are instead also rod dependent. And then you can run the mean field machinery to obtain some coupled equations for the modulus and the phase of the condensate wave function. And at late times, which is associated again to this having large number of quantity of condensate, of course, at the background level, we find a matching with GR, where the macroscopic couplings are defined in terms of the group field theory ones. But at the level of perturbations, when we go in the deep superhorizon limits, so when the momentum of these perturbations is very, very small, we have a perfect GR matching. But as soon as we turn these perturbations on, there's some unphysical and concerning behavior of these spatial derivative terms. And before I tell you how this problem can be solved, let me actually consider, instead of late times, let me consider early times. Because we've seen from what Daniele told us that at early times it's where we have singularity resolution. So we do expect some fancy quantum gravity effects happening at early times. And we can still study this deep superhorizon limit in which at late times we have the matching with GR. And looking at deep superhorizon modes is also particularly helpful because there's a way to systematically derive the equations for these perturbations in any modified gravity theory. And you can obtain the perturbations equations also by perturbing the background equation. So we were wondering if this is actually the case also for our group field theory emergent perturbation equations. And in fact, we found no matching with any modified gravity theory at early times. And we also find that our equations cannot be recovered by perturbing the background ones. So our interpretation of this mismatch is related to the fact that, in fact, when you follow either of these approaches, what you're perturbing is the metric. And that is an emergent quantity from the perspective of group field theory. In our case, our perturbations are at the level of the condensate wave function. These, in principle, are two variables. And what happens is that at late times, this phase variable is frozen and completely decoupled, while at early times it's dynamical, and it's particularly important for the dynamics of the modulus as well. So it's just a different set of degrees of freedom, and which might generate this kind of important mismatch. So finally, let me tell you about that unphysical behavior of spatial derivative terms, and let me specify what I mean with unphysical behavior. Because these spatial derivative terms don't behave as if they were spatial derivative terms with respect to minimally coupled masses and free rods. So we did realize that in order to better understand this issue, we needed a more concrete handle on the causal structure of these theories. So we consider instead an extended Barrett-Crane model where you have explicit access to the Lorentzian properties. And in particular, we consider the two-sector group field theory based on space-like and time-like tetrahedra. And that also not only allowed us to better couple these frame fields, but also allowed us to look at different kind of condensate states. And let me tell you what this equation means. So we still have a space-like condensate, which is this term here. We also have now a time-like condensate, but these are our background quantities. So the condensate wave function is homogeneous relationally, and they're peaked because we want to implement this effective notion of relationality. However, perturbations now encode nearest neighbor in a relational sense to body correlations. We can have space-like space-like correlations, space-like and time-like correlations, and time-like and time-like correlations. So you can run the mean field machinery again. And what happens is that first of all, we have two mean field equations for three variables, which is not a good start. But what happens is that if you look at late times and you require that this physical behavior of the spatial derivative terms is satisfied, then this fixes the dynamical freedom completely. And you can actually look at the equations for the dynamics of this volume perturbation and the scalar field perturbations. And what happens is that there are quantum gravity corrections at relationally trans-Planckian scales, but there's GR matching at larger scales. And also let me mention that for some observables and for some specific solutions to the GFT equations, it's actually almost impossible to distinguish between GFT and GR results. Okay, so this is a brief summary of the story. Let me just emphasize what are the main results. And so the first is identification of these inhomogeneities as quantum correlations, which really goes towards the idea of having non-trivial geometries coming from quantum entanglement of the fundamental degrees of freedom. And we did find the dynamics for these perturbations, which is trans-Planckian relation, which has some quantum corrections in the trans-Planckian regime. And this quantum gravity emergent dynamics seems to differ from any modified gravity theory, possibly casting some doubts on the rewriting of these dynamics in terms of effective field theory in that regime. And these are some steps that we would like to take in order to go more towards observations. So thank you very much.
Okay, thank you, Luca. Questions?
So this related to the morning talks. If you have inhomogeneities in trans-Planckian or close to Planckian, you can check if there's a consistent causal structure. Have you done that, or can you say anything about it?
What do you mean consistent causal structure precisely? Like if they satisfy some causality relations?
Well, you have evolution equations. Yeah. If there's a
like,
is it a standard wave equation?
It's
or
a standard wave equation in the relational frame, though. I can actually show you the form of the equation. It's a little bit of. So this is for the comoving curvature, kind of the comoving curvature. This is another important thing. This is the relational comoving curvature, or a variable that really looks like that. We're missing one observable to actually turn it exactly into the comoving curvature. And this is the equation for the comoving curvature. The GR part will be this one, and this is the quantum gravity correction. So it's still the same kind of hyperbolic structure for the equation. And here there are some plots, and actually that's what I was telling you before, that depending on some initial conditions, for this observable, the mismatch between GR and group field theory is very, very small depending on the value of these initial conditions.
Okay, then let's thank Luca again.